How long is it?
Usually 40 minutes.
40 minutes?
Yeah.
That's a good idea. Yeah, I should tell. No, I can check.
It just makes it easier. But that's when they'll bring a scooter and scooter.
I think that, because it might be slippery. I might have told you. Yeah, that's what I'm thinking.
Yeah, I just brought one out for you guys. I got you. Your beer's coming right now. Thank you.
Like a thing, like I've never.
Alright, welcome everybody. We're going to get started. Alright, well, welcome. Oh, thank you. Welcome everybody to our Science on Tap. It's the last Wednesday of every month. If you like it, you can come again. So it's put on by WISE, which is the Women in Science and Engineering organization at UC Santa Cruz, and we do outreach events to the public. And today we are going to hear from Kyle Broach, who's going to be talking about the Yucatan climate through his microfossil work. And let's give him a big round of applause.
Thank you, Regina, for that introduction. To see a world in a grain of sand. The opening line of...
Can you turn it up?
Turn it up?
Yeah, we can do
Yeah, Regina can definitely do that. Thanks, Regina. Otherwise, I do have to speak directly into it.
Okay.
Suspense.
The better?
Testing. Is that better? Can you hear me better now?
Thank you.
All right, excellent. To see a world in a grain of sand. The opening line of William Blake's Auguries of Innocence may well have been referring to the sands of time. And they tell a very deep story of the rise of mountains, the fall of glaciers, over Earth's 4.6 billion year history. My name is Kyle Broach, and I am a graduate student at UC Santa Cruz in the Biogeochemistry lab. And from an early age, I was always really interested in geology and the outdoors. And I always considered the Earth's surface to be a book, the many layers going back in time to be pages with which we can read. But translating the language of Earth history is actually pretty difficult. And it turns out that you need special tools to do so. Those can be found in what is known as geochemistry, which is the chemistry of the Earth. So using these tools, we can understand as we go back in time how the Earth was, and in doing so, get a glimpse of what Earth's future may look like. Oops, wrong way. Why do we want to do that? What is the motivation for this kind of work? Well, these are images of California and the Sierras from 2013 and 2014, and they show snowpack in the Sierras between those 2 different years at the onset of our current drought. What we really want to know is, how often do events like these occur? Does that frequency change? When they occur, does the severity change? And answering those kinds of questions about the past gives us enough information to help model going forward. So for this particular talk, we'll be looking at climate of the past and the present, and looking at studying climate to understand impacts on modern society. I will spend a good bit of time not just talking about the data itself and what it says, but also on how we collect this climate data. Because again, those tools of geochemistry, or the chemistry of the Earth, are a little difficult to interpret, and so we'll actually step through how we get this data, and then interpret what it means in the context of the Yucatan Peninsula. What you see here is a video of Earth's global average temperature from NASA. I'll take a step back so the friends of this table can see. And what you're seeing is that orange are high temperature anomalies, blue are low temperature anomalies. But all of them are showing increases in temperature on a global scale. This is well established, this is something that we know, this is something that we can observe. And what you'll see is that the Earth overall is becoming redder and redder and redder. And this goes up until 2011. But how climate change on a global scale is manifested on a smaller regional level is more complicated. It's less understood. The reasons being that on a global scale we can measure average temperatures as they rise, but what really determines climate on a regional scale is the amount and timing of precipitation, when and how strong winds occur, how strong your seasonality is from season to season, month to month if it's on short timescales. Looking at these 2 images here, one is from California from during the drought. It's the Oroville Reservoir in Northern California. So you can see that it's at a very low level. And the second image is of Hurricane Harvey and Houston in August, only last year. So places that tend to be more Mediterranean or slightly drier may actually continue to become drier. Places that are warm, humid, wet may actually get wetter. These are particular examples of weather, so I'll actually be talking about climate on broadly. But when we look at these kinds of events, what we want to know is, how is a particular strong weather event influenced by trends in climate over time? Even though we can't attribute any one event to climate change itself, the strengthening of temperatures in the atmosphere, of global circulation, is more likely to will make these events more likely to occur. So this is the first figure that I want to talk about, and it's from a study in 2012 by Chu et al., and what it's actually looking at is seasonality. So these 2 graphs on the left and on the right are looking at roughly the last 20 years of precipitation data across the US. On the left, that is looking at the time period 1980 to 2000. What you may notice from this is... Sorry. Okay. What you may notice from here is that across the equator, we tend to have these red zones. And as you go farther towards the poles, they become blue. If you go by the scale, it's on the bottom of the map, what that's showing you is the annual range in precipitation. So for any areas that have seasons, a wet season and a dry season, how much rain actually occurs in that wet season or in that dry season. The more red this graph, the more your extremes are. Some areas do not have a whole lot of seasonality. They looked at the same data, also including the first 8 years of the 21st century, and what you might notice is a marked increase in the amount of red that's occurring in the Eastern Pacific and in Central America, which I'll point out. So you see a lot more red here in the Eastern Pacific as well as in Central America. What they are showing from this study is that even on a global scale, we might have increases in temperature. Where we have seasonal rainfall, where you have a distinct wet and dry season, you are getting more rain during your wet season and perhaps even less rain during your dry season and the interim, which means that a lot more of your precipitation comes all at once in one big burst, dropping lots of water that may just run off back to the ocean. And this is important because it is the regional climate that's actually impacting water resources, or flooding, or infrastructure. All of the things that regional and local communities depend on are influenced entirely by the regional climate that actually dictates the daily weather patterns. So that was in the modern. We can study the last 20 years of data or the last 40 years of data, but it becomes much more difficult as we go farther and farther back in time. The simple reason is that we simply didn't have thermometers 1,000 years ago. We didn't have barometers 10,000 years ago. So we have to use what are known as proxies. And a proxy is a substitute in the natural system that we can use as a measure of some process of the past. We'll go into these a little more in detail in just a bit, but in particular, the proxies that I'll be talking about in this study actually track groundwater. So we can't go to 1,000 years ago and measure the groundwater, but what we look for are sources that record signals of that groundwater. If that system is similar to the modern system, we can measure modern groundwater, we can measure the modern chemistry, and now we have a tool that actually helps us calibrate and reconstruct the past. Particularly in this example, we'll be looking at the abundance of certain elements that occur in groundwater, as well as isotope signatures, and I'll come back to that in a bit. And with these, we can establish a record that's 5,000 years long for the Yucatan Peninsula. And given that time occurs on millions to tens of millions to billions of years, if we really want to understand regional climate, we need a longer timescale perspective, which is what these proxies and records allow us to actually do. And why that's relevant to the modern system is that in the past we have seen in multiple places, but most notorically in the Yucatan Peninsula, collapse of civilizations that really rely on these water systems, and in particular we'll address some of the Mayan cultures. So, to give you some background for this region where we are in the Yucatan Peninsula. So it is the section of Mexico that it points into the Gulf of Mexico. And the Yucatan is what is known as a karst platform. It is made up of the rock limestone. Now, limestone occurs in a lot of places. It's very common throughout Florida. And it's a rock that dissolves very easily in the presence of rain or other water sources. And so as a result, the Yucatan Peninsula, as with Florida, is full of sinkholes, is full of caves, is full of conduits that transmit a lot of water whenever it rains on the peninsula. And the Yucatan Peninsula itself does have a fair bit of rainfall. So what you're looking at here is a modeled simulation of rainfall across the peninsula, blues being high precipitation at about, I think, a few feet a year, down to reds in the upper corner, which are much smaller, maybe tens of inches per year. And you can see this across the entire peninsula. Now, the Yucatan has very strong seasonality to when it rains. You can see that in the bar graphs as we move across here. These peaks represent January through December, so there's 12 of them, and the bulk of the rain is actually coming from about June through October. So the summertime is very wet in the Yucatan Peninsula, the wintertime tends to be very dry. It's sort of the opposite of California. Once that rainfall lands on the peninsula, which again is full of holes because it dissolves easily in this limestone, then the rainwater percolates very quickly down to what's known as the water table. It's a layer of water underneath most of the rocks. The image here shows simulated groundwater flow lines for when rain enters the peninsula and where it flows towards the coasts. The blue lines here represent each of those modeled lines, and the residence time, or how long a particular rain event stays in the peninsula, is about a year long. So what that means is that we can actually follow pulses of rain. For example, if you have a hurricane move across this whole system, you can follow that pulse of water through different wells, through different aquifer sources, and watch it go to the coasts. So we've established how long it takes, and it's very quick, which means that any drought or rain events are immediately passed through the cave system, and it's quite ubiquitous. So this entire cave system moves all this water to the edges. The white here represents higher elevations, the black represents lower elevations, and water flows downhill even when you're underground. So it's still following that topography, and where it comes out at the coasts here actually represents springs. These springs intersect with the ocean, so they're known as submarine groundwater discharge. It's a fresh or slightly salty spring that is discharging water into the surrounding ocean. And this is a schematic diagram of what that looks like. So this is from a paper in 2017. Here we have the Yucatan the karst topped with all of its trees and vegetation. Throughout the peninsula, we have these cave and conduit systems, including some of these sinkholes. And when it rains, that water percolates down into a freshwater lens. And that lens sits on top of some salt water, because freshwater is less dense than saltwater. And as you rain on this peninsula, more of that water is going to flow towards the coast. So this is where we're getting that groundwater discharge. So let's back up one more time. If we look at that map of where this groundwater flows to, you'll notice I've highlighted a red box here, which is our field site, which is known as Celestune Lagoon. And this is what it looks like. Those are flamingos. Celestune Lagoon is a very neat place. It's actually known as a biosphere reserve, which is sort of like a biological national park for the Yucatan Peninsula, which is incredibly rich with diversity, especially of birds, but also of vegetation and insects. So this field site here, you can see, is fairly shallow. The flamingo are standing in it. It's only maybe a foot or two deep of water. And in the background vegetation, you are seeing mangroves. So this system actually thrives on water that is somewhat salty. Normal ocean water is around 35 parts per thousand in salt. It's like percent, but instead of out of 100, it's out of 1,000. And if normal water is 35, this lagoon is around 15 to 20. And mangrove systems thrive in these areas. It's very rich habitat for brine shrimp and other crustaceans, which is what gives flamingos their pink color. And this is one of the largest flocks of flamingos that live in the Americas. So at field site, it's especially good. If I backtrack one more time, you'll notice that these flow lines have water coming from the highlands that intersect that field site, as well as water from the lowlands intersecting that field site. So essentially, this lagoon system is sourcing water from the entire peninsula, so that when it rains, all that water is following these channels and conduits coming out of this lagoon site, which ends up being very rich habitat. And so that's very useful for the study, and I'll get to that and why. This is looking at a map, again, of Celestune, but this time I've turned our map 90 degrees, so that north is to the right. So now you actually have sort of a north-south axis moving from right to the left. And it's showing you, in purple here, where we would collect water samples. In black here, where we would collect sediment samples. And in these red crosshairs are where we collect sediment cores. So this is a semi-enclosed mangrove estuary system. Estuary being that it has components of freshwater and components of saltwater. It's semi-enclosed. You can see the geometry here from the ocean all the way up to the head is more or less a narrow straight line, and that keeps a lot of that spring water in the system. The center of the lagoon is full of these groundwater springs, as is the upper lagoon up here. And so it results in very nice salinity gradients. So if we take a look at what some of that actually looks like, we are looking at the latitude along the lagoon. It's the same. These are to scale. And this is the value of salinity. And again, 35 or 36 is roughly the value of the ocean. And it goes down to as low as 12 or so in the head of the lagoon. So this salinity gradient is showing you that you have groundwater coming into the system, and it's mixing with some of the salt water along the ocean to form this nice linear trend. Now, during some seasons, because the Yucatan is seasonal, when you have decreases in rainfall, these values up here all shift up, which is saltier. When you have increases in rainfall, all the values shift down, which is fresher. That's on a seasonal scale, but you could imagine over long periods of time, if you have extended droughts, you would have less groundwater coming into the system. So the whole system would stay saltier. The opposite would be true as well. Huge rain events would flush fresh water into the system, so the whole system would become fresher. And this is all due to the behavior of these groundwater springs. So, how do you go and collect all of that? You get in a boat, and you go to the lagoon. So, this particular field expedition is from 2015, during June, so right at the tail end of the dry season, before the wet season. So you figure out where those springs are, and you go and collect several different samples, including within the lagoon itself. recall that it's what's called a fringing mangrove system, which means that mangroves tend to live all around the edge of it. You can see here that the center of the lagoon is pretty open. That vegetation in the distance are the mangroves, and if you go to them, you can actually navigate around those mangrove roots. Mangroves are a particularly interesting plant type. They are able to live in somewhat salty waters, and they actually excrete these salts. So they're not limited by the amount of fresh water in the system, but they do require some fresh water. They cannot live in purely saline ocean environments, but anywhere that the salinity is maybe 2/3 to 1/3 of the ocean, they're very happy there. If you follow this path all the way to the back of the mangrove system, then you start to see these groundwater springs. This is an example of one. You can see how incredibly blue and clear this water is because it does not have a whole lot of dissolved components in it. And the roiling right here, this is from the water actually coming up from a spring site with enough force to force all of the water away from it and ripple the surface. Very similar to any sort of fountain that you might see. So whenever you find something that is kind of out of the ordinary for a system, naturally you want to grab a sample of it. So you jump in and you grab one of these water samples. And this allows us to actually measure the groundwater coming directly out of the platform before it reaches and mixes with the rest of the lagoon. In addition to water samples, we want to collect what are known as core samples. So in this case, these are some of my collaborators, and in the open lagoon system, which you can see here, it's pretty shallow, and you can stand in it and take essentially a large PVC pipe and push it directly into the sediments. When you pull it back up, this is what you get, and you might notice that it kind of looks like it's full of sort of a chocolatey or coffee color. Those are all the sediments of the lagoon. So going back to that analogy of the surface of the Earth being a textbook full of layers that we can read, well, think of the entire surface of the Earth actually more of a library, where there are different archives, there are different books that we can read, all requiring slightly different languages to translate, but something that we can do. So you take your sediment core here, and in this form, it's not as useful. So we have to do a couple of things to it. One is to take it to a lab, and you go ahead and cut it in half. What you're seeing here is an image of what's called a core logger. And so these are two different videos showing that the core gets pushed through a series of instruments, and those instruments are doing a number of things. On one hand, they're taking a photograph of the entire core. So imagine a panorama, but instead of you having to move the camera, you simply move your object instead. It's also taking measurements of the density of sediment. We'll go back one just so we can actually see that again. It should start again. So it's taking measurements of the density of sediment, how fast sound waves move through those sediments, and also how much magnetism these cores have. For example, if you have bits of iron from the atmosphere, all of those settling into these cores can be measured, and this is all really, really useful data. Once you get all of your images, you end up with something that looks like this. These are about 12 or so different cores from along the lagoon system. Each of them comprised of slightly different parts, because when you get cores, you have to break them into sections as you break them up. But you'll notice that there are a variety of colors and a variety of textures to all of these sediments, which is incredibly useful to start first visually with what these look like, and we can zoom in to some of these. So we're starting to zoom in closer and closer to these archives of past climate. If we zoom in really closely, then you can actually see these are incredibly detailed photographs on the order of, I think, 50 or 60 megabytes per image. And they can start to show you some really high detail. What you're actually looking at here is a transition from these darker sediments into these lighter sediments. That's actually a measure of carbon. So how much carbon gets stored in the system, and you had some particular event here that changed that. Notice the texture as well also changes from fine-grained to this coarser material, and then to finer material once again. So when this goes through the core logger and we measure a lot of our data, we can actually see, we can plot that directly in our cores. This is actually a measure of density. So you can see that these sediments here get denser at this particular boundary before carrying on. Why do we have to spend so much time looking at all the characteristics of these cores? Because it turns out that when you get these cores across even a lagoon, how quickly the sediment settles in the water column, or what's known as sedimentation, or what storm events come through to wash a lot of it out, changes depending on where you are in the lagoon. Towards the ocean, you might have more hurricanes. Towards the head of the lagoon, tends to be more protected. So you actually need all this data so that you can start correlating all of your records across an entire lagoon, which is what you see here. So I've put together an image from Google Earth, and you're again in that north-south latitude of our lagoon. This is the head of the lagoon with a lot of its springs, the mouth of the lagoon that opens to the ocean, and at each of our core sites you can see that we have the cores going down for those sites. So it gives you an image of not only the surface of the lagoon, this is all we see of the lagoon going back in time. So it's rather a less complete picture, but that's what we are working with as we interpret the past. And all of these lines here represent what are called tie lines, or these are the sections where these should actually be the same events based on the density or other characteristics of the sediments that show these should all be correlated. So you can see how choppy this is going across the entire lagoon. This is done for any sediment across anywhere in the world, whether it's the deep ocean or shallow lagoon systems. So once we actually have our sediment archives, then we can take a thin section of any one of these, take a centimeter slice, rinse it off, and this is what you're left with. It's just shells. And this particular site is full of clams, of snails, of a lot of organisms that produce these hard calcium shells. You go through this to an even finer scale, and you pick out just what are known as foraminifera. Foraminifera, or forams, as seen on the shirt, are single-celled organisms that produce a carbonate shell. And this graph here, this is showing you essentially a catalog, one that I very painstakingly put together, of all the different species that you find, which is really useful because different organisms like different environments, so the total ensemble or assemblage of organisms you find tells you something about a lagoon. In this case, a modern system, we can observe that it's somewhat brackish, is full of mangroves, has groundwater. This assemblage of species loves to live in that system. If we zoom in even further to just our first square, we finally start to see our grain of sand. So this is the species known as Ammonia parkinsoniana, and to give you a slightly better definition image, we're going to look at a scanning electron microscope, which is here. It is no bigger than the thickness of your fingernail. This is 500 microns across, which is to say half a millimeter, which again is just as thick as your fingernail itself. This is the archive of 5,000 years worth of history in the Yucatan Peninsula. Here you're looking at the top of it. This is known as the spiral side. It starts building these chambers. So it'll build one chamber, then another, and it continues to spiral around. It looks somewhat similar to perhaps a nautilus, which most people usually experience. If you turn it on its side, you'll see that it actually has a different top, which has this spiral shape, and a different bottom, which has this creviced underside. That's unique to this particular genus of foraminifera. But again, this is what is living in the lagoon, and there are many of them, on the order of millions. I'm very lucky in this lagoon that they exist in such abundance. But you go through, you find each of these, and you actually pick them with a paintbrush to see what they record. Now, why this particular species? Why this one? It is extremely tolerant of wide changes in its environment. So remember that I said that those springs bring fresh water to our lagoon. They make it slightly fresher. If you have droughts, it gets really salty. Most organisms do not like those changes. Think about saltwater fish. They really can't tolerate freshwater conditions. Same for river or lake fish would not be able to do the reverse. This can withstand really large changes in that environment, which means that it's always present going down through our sediment core. So it's a very continuous existence throughout the core, which means that when we see changes, this will record them. Now, how do they record this? Well, this is where we're going to start jumping a little more into the chemistry side, so where all of this information comes from. So I have here an image of the periodic table full of a wide swath of metals and nonmetals, and I'm going to highlight just a few. So we'll talk about some of these here. Mainly carbon, nitrogen, and oxygen, and then also strontium and barium. These exist throughout the Earth. They're somewhat abundant in the crust, and with these, they have particular properties in plants, so carbon and nitrogen are very abundant in plants, Oxygen is going to play a role in our water, and strontium and barium are going to play a role coming from our Yucatan platform itself. So, to look briefly at this schematic diagram, what we're going to have to delve into are what are known as isotopes. So, with these elements here, every element has a certain number of protons in its nucleus. That's what defines an element, which one it is. But they can have different masses, so you can also change what are known as neutrons in the nucleus to have more or less. And all of the different elements here do have different isotopes. Some are more stable than others. Non-stable ones are known as radiogenic isotopes. You may be familiar with radiocarbon, for example C14. We can use that to date things going over time. Uranium is another very common non-stable element. And oxygen is very abundant in oceans as water. And what happens in the ocean system is when you heat it up and you start evaporating water, those light mass oxygen isotopes, they preferentially leave. It's much easier to spend less energy lifting something light than it is to lift something heavy. So the light ones go off into the clouds, and whatever the heavier ones stay in the ocean itself, which is known as enrichment. Those clouds move over any sort of landmass and they start to rain. But that rain, that water that's there, is not the same as what was in the ocean. The ocean now has more of the heavy mass water, and what's raining on the peninsula has light mass water. So that's one signature. Once it actually is on our platform, it sinks into our ground. Remember in the Yucatan, it's like Swiss cheese, so that water sinks into the platform, and think about how cave systems form. They dissolve. So water's moving through the system, it's slowly dissolving some of the rocks out, and those rocks have a lot of strontium and barium in them. And as it flows through the groundwater system, it comes back out at the coast as our springs. So we have 3 different tracers just from this natural process of what is rain. Rain is evaporating, taking one form of oxygen into the clouds, it rains out into our platform, and then it's dissolving these other minor or trace elements in our rocks, and the water that comes out of the springs is elevated in them. And that's what I'm showing in here, that as this water is moving through the system, it's actually bringing with it these very distinct tracers, and that's what we call them. They're isotope tracers to these spring sites. So when you saw me diving into this, getting a specific sample, what I wanted to know is, what is the end member for water that's coming through here? What is the oxygen isotope signature? What is the strontium signature? And what is the barium signature? How does that relate to climate over time, or to the foraminifera? So if we zoom in on some of these sediments from the system, this tiny circle here, to point out, that's actually one of the foraminifera. It's the Ammonia parkinsoniana. Again, as thick as your thumbnail. These are made of calcium carbonate, just like clams or snails. And that mineral, in particular for these, is known as calcite, and this is an image of what that looks like. If you zoom in on calcite, it's made up of a series of elements. In this case, it's calcium, carbon, and oxygen. But this doesn't happen in a vacuum. This Ammonia parkinsoniana, any foram, any clam, needs starting material in order to construct a shell. So this is happening from the water above it, and it's taking the calcium and any carbon and oxygen to build it. But it's not as picky as you might expect. It will take whatever will happen to fit into the structure. And if that happens to be strontium and barium that are near the system, it will incorporate them into these laticites. The green here is calcium, the black is carbon, and the red is oxygen. All that matters is that the more of the stuff you pump into water, that's the more of what's available. It's going to take it. And so within this foraminifera, it tends to have more barium, strontium, and the particular isotope of oxygen where it's more abundant. Well, where is it more abundant? Near the springs, or if your springs discharge a lot more of that water to your lagoon, then it's more abundant across the entire system. So here's one other video to look at how long this process is, just to get to the data point. Thankfully, most of it's automated. So we actually take those foraminifera, you pick out a number of them, you dissolve them, and then you put them through an instrument that will actually show you all of the different elements that are there. So that's part of this process, to actually get to what is in the foraminifera. Thankfully, we have auto samplers that do this for you instead of doing it by hand. And this is what that data looks like. So I spent a bunch of time showing you how we get to this point, but it's really important to understand when we interpret climate records, where they're collected, how they're collected, what are the processes that create sediments. it influences our final result, which we need to understand if we are to say this means drought or this means flooding. So we are looking once again at our field site. Small image at the top. All of the purple spots are any water samples. Black and red spots are sediment samples, with the red ones going deeper into the sediment column. Here, this first image is looking at our oxygen isotope values for our water. So we go through the modern system when we collect our water. First thing to note is this dotted line represents the average value of the Gulf of Mexico, so what you would find just within the Gulf of Mexico. These values here that are slightly elevated, at slightly more what are known as positive values, suggest that the whole system is not exactly at the same as the ocean. But where you get towards these springs, these yellow points, notice that they are much more negative. This is that light water I was talking about. And as you go higher into the lagoon, these values actually get more positive with some spread. So what does this graph actually mean? It shows you that where we're near the springs, as expected, we have the light water that represents rainfall. So we already are pretty sure that this water is coming from rain. It's not some other system bringing water to the environment. Where we go to the upper lagoon, if we look at this whole line that's all slightly elevated from here, it suggests that the water is heavier in the lagoon overall. How do you make water heavier? You remove the light stuff by evaporation. So what's left stays heavy. So what this graph is showing you is that in the upper lagoon, we actually have a lot more evaporation going on than we might otherwise expect. But if you were to correct this for evaporation and bring all of these points back down to the rest of the lagoon, these points here that are towards the bottom would once again become negative, showing that they are from the same spring sources as our center of the lagoon. So that's just the water. If we look at the foraminifera themselves, we can see that they actually follow a very similar trend. As you go towards the spring sites, they are actually becoming more negative 3.5 or so. And as you go back towards the upper lagoon, we see that evaporation or towards ocean values. So this modern system is actually how you would calibrate your tools. So if we recap on that, negative values or yellow values represent negative values, which represent rainfall. The higher blue values up here represent evaporation. But even with those multiple systems going on, we can take the foraminifera that live in just the top 0 to 2 centimeters of our sediment, measure them, and figure out what is the actual offset. Which means that when you take these samples back in time and get a value, you can recalculate what the actual water value should have been. And from precipitation data, we know how much rainfall does that actually mean. The same is true for the strontium. So strontium in this case, again, looking along our lagoon, these are values from the strontium to calcium ratio in our foraminifera. What does that mean? Well, the forams, remember, mostly like calcium. They build these calcium carbonate shells, but if there's more strontium around, they'll pull it into their shell. In the upper lagoon, where we had most of this discharge coming from the platform, they have a lot more strontium relative to their calcium in their shells. And it decreases as you go towards the ocean. And with the salinity of the lagoon, we have high salinities towards the ocean, once again decreasing towards the upper lagoon, and you can see that these are in inverse trends. They are inversely related, which means that this is actually a salinity tracer. Wherever you have higher strontium values in your foraminifera, it actually means lower salinity for your whole system. And you can see again from, this is the upper sediments of our system, this is the water column immediately above them, and they are directly related. So if you were to only go back in time and use these values from forams that you measure, you can recreate what the salinities should have been. Why do we do this? In two different ways. Recall that oxygen 18 may be affected by evaporation. Salts in the ocean don't evaporate, so this is going to stay in the same concentration even as we leave, even as any light water leaves. So now we can actually start applying this going downpour. So in our lagoon, this is looking at the oxygen values of our water. And here there are two things to note. One, these warm colors, red and yellow, represent the upper lagoon. And these cooler colors, blue and green, represent the middle lagoon. And you'll notice that over their entire history, they're always slightly offset, which by these values, meaning that the warm colors are actually heavier in their water, and the cool colors are actually lighter. that suggests that over this 4,000-year history here, the lagoon has not changed in its geometry, so that you've always had an enclosed head and a slightly more open center lagoon that's giving you these values. What I want you to focus on is the actual wiggles of the lines themselves as you go back in time. And what these mean, if negative values mean more rainfall and more positive values mean less rainfall, then as you decrease, this is actually a period of wet times, and as you increase, it's a period of dry times. Which we can actually see right around 1,000 years, we have a period that suddenly really takes off in terms of the decrease in rainfall. You can look at something similar with strontium, but it's not nearly as prominent. Part of the reason for that, if you look at these scales here, strontium is much smaller, 2 to 3.5, not nearly as sensitive to these changes in groundwater discharge as the oxygen. But they also tend to show you these overall trends, which might appear to be a steady increasing of precipitation. So remember that seasonality that I talked about, that over long periods of time, your changes of precipitation between seasons can actually change. But in addition, you actually still get these extreme droughts that happen on top of that. Briefly, to turn this into actually salinities, these plots here show very similar information. This is strontium to calcium in the foraminifera and the barium to calcium in the foraminifera. Remember that in our modern system, we can actually take these values and have them correspond to a particular salinity of our lagoon and create what is known as a calibration line. So essentially, I want to take what is my actual strontium and my foram or my barium and turn them into salinities. And that's how you do this. These are actually measures of salinity. Remember that the ocean is around 35. Most of these values, these are colored by latitude, so these darker colors here are the lower lagoon towards the ocean. These lighter colors are the upper lagoon towards the head. And you can see that, well, again, over their whole history, this time is on the x-axis, their whole history, the ocean ones are always more saline, and the lagoon head are always more brackish. But what we really want to focus on are, when do we have these excursions? When do we see a change from the trend of a consistent environment to perhaps an influx of water? Or, in the case of the mid-lagoon sites, basically a spike in salinity. These are periods that you would expect to see drought. You make water saltier in the system by reducing the amount of fresh water overall. And in particular, the last 1,000 years have been incredibly variable for this site. The next step you would do is correlate that across other records in the entire peninsula, which people have done, and I'm just going to show them to you here because there's a lot of records that people do, and I won't go through all of them, but the key point to mention is that you use multiple systems because across a whole region you have different things going on. Different areas might receive precipitation, different areas might have slightly more intense droughts. You can think about this in California and how its climate over the entire length of the state changes. And the reason why we care about this particular variability, this is here looking at the droughts, this is right at the occurrence of the collapse of the Mayan civilization. So there's an excellent article from Peterson and Hoff in 2005 in Scientific American that looks at what the Mayans are doing and writing about during this time. And two things to note, well, the main thing to note is this image that's on the right actually represents one of those sinkholes. Now remember that on the peninsula when it rains, that water table is pretty high, so these sinkholes have a lot of water in them. We have found evidence of the Mayans actually building stairs deeper and deeper into these sinkholes to access the water table. And what that implies is that over decades, that water table is sinking lower and lower and lower because you have an increased drought at this time. And the implications for the modern is that the Yucatan is actually expanding incredibly rapidly. Tourism is on the rise. There's a lot more development in both agriculture and commercial systems. And in fact, in 2017, they had a record-breaking 3 million tourists visit the area. So at a time when, over 1,000 years, the rainfall is actually variable, coupled with the fact that on the global scale, our temperatures are rising and increasing the extremes of our rainfall, we have more people in one place using water resources that are only recharged once a season. Perhaps that sounds somewhat familiar. And the conclusions that you can draw about the Yucatan Peninsula from this long history of work is that Yucatan groundwater is a lot like Sierra snowpack, that it does recharge only once a season, that there is increased demand for that in commercial and residential systems, and that's also drought sensitive. If you miss your water for one season, it takes a long time to catch back up to it. And that actually requires constant conservation and a very different management schema than perhaps what we're used to, which is why we do this kind of work. What is the frequency at which this happens, and how does that change going forward? Because then you can understand in what time scales do you really need to do managing of your resources. So we use regional climate models, we make regional climate models using this proxy data, and it actually helps us understand the regional scale. So even if climate warms overall, it's on these regions where you might see changes in precipitation, whether it's through drought or flood. And because of the variability, you look at the variability, so how this happens from year to year, and the drought periodicity. How often do these actually occur, and will that occurrence increase? And it has huge implications for the well-being of communities that depend on these resources, whether they're in the Yucatan Peninsula or California. And I would actually like to send a reminder that California snowpack this year is at 30%. So when you're looking at annual variability, even if you have a single storm, the long-term trends might actually suggest you need to do something different in your overall conservation and management. And that might actually be considered as the new normal for how we conserve our resources going forward. As the saying goes, it takes a village to raise a thesis. There's a lot of people that have really helped with this project, a lot of particular students that have been very useful, and many, many organizations. Actually a lot in California as well. There's a lot of work done in the Bay Area. And with that, I'd like to take any questions that you might have.
So, kind of the very recent historical recorded record has very high resolution because we can record it, right?
Yes.
So we can record things at a daytime scale.
Yes.
Or even better than that in some cases. So, in the sediment stratigraphy that you're looking at, what's the resolution do you think that you can get at that is the finest division of time?
For these particular sediments, every sediment interval, centimeter interval, excuse me, represents about 20 years. So you actually get multi-decadal measurements. There are other records, and I pointed out one very, very briefly, like cave records, or speleothems, as they're known, that are incredibly high resolution. So this is a cave record here, showing the growth lines, and you actually can measure the oxygen isotopes, and each of these may even be seasonally resolved. You can actually figure out how much rain occurred in the winter. The difference is that these are incredibly site-specific, so you only get cave growth, or speleothem growth, where your water happens to be funneled to. And in a regional context, if your rain shifts, you might not be recording it. You could have just as much rainfall, but it's very specific. And with this lagoon site, it's a 20-year resolution, but it's integrating over the entire peninsula because all of that water is coming through these cave water systems.
Sure, but it does mean that with those forams, it's kind of averaging.
It is.
What's happening during that 20-year time period?
It is absolutely averaging what's happening during that 20-year time period. But again, what you want to look at overall are the trends.
Sure.
And so you can figure out these periods where it does increase or decrease. The other advantage of the site is it's the longest sedimentary record of the Yucatan Peninsula, which again has other things that get recorded into it. So it is an average, but it is higher resolution than perhaps some other records that we might have. I've not looked at it for this site.
Can you repeat the
So the question is, how does ocean acidification impact foraminifera as they build their shells? So these are calcium carbonate shells, just like corals or other calcifying organisms. I have not looked at that for this particular site. I would expect, as with most organisms, it should make it more difficult because they're trying to build this calcium carbonate shell in an acidic environment, which is dissolving away. I think in the open ocean, where we do have foraminifera that actually live in the water column as opposed to deep sediments, we have seen that they have been making thinner shells, and at least that's confirmed by some lab studies. So it probably would make it more difficult like most organisms. But you can actually measure that through boron isotopes, which I didn't get into in this site, but that's actually a proxy for pH.
Is that all?
Yeah.
So,
just in your methods, you showed your map of your sampling, and sometimes you collect water samples, and sometimes you collect water samples, but not really in the same places. And so how do you make the choices?
That particular map showed some the data that was in the study. I do have other years where they are actually collected simultaneously. Usually it's best to collect a sediment core and the water sample in the same place. Part of the difficulty here is that because it's a biosphere reserve, you are limited into where you can actually go to minimize disturbance of a lot of the organisms in the sediments that the flamingos feed on. So you tend to make those choices in part along the length of the lagoon where you can actually get the water samples and the sediment samples. But because it follows such a really nice linear trend, then as long as you get enough data points, the extrapolation between them is really, really accurate.
I may have a dumb question here, but has anyone mapped the underground cave system? And is it possible that the dynamics introduced by that underground cave system may skew your results?
Excellent question. So the question is, has anyone mapped the underground cave system? And if there's a change in it, or how does water flow through it, does it skew these results? There have been a lot of attempts, there are a lot of attempts to map the system, and we're still discovering more. I think just last year we discovered that two of the largest cave systems actually, they communicate, so the water actually flows between them, making that the largest known cave in the world, I think of 217 miles long. So extraordinarily large. So we're still trying. We don't know exactly where all of these go. The second question is, what happens if that cave system changes? You would, if, for example, you have a cave collapse that blocks water, you would absolutely expect a shift from near the spring. You'd have it would appear to be a decrease in groundwater and a decrease in rainfall. I only showed 3 of the proxies that I use here, but actually I measure 14 different trace metals, 7 different isotopes, and a whole suite of foraminifera. If I go to a little bit of the data that shows that, there are other proxies that you can use. One of them is known as a forum assemblage, so you count the community of organisms that are there. Some of them like the really fresh conditions right near the spring, and others don't. And so what would happen if your spring completely shut off, you would see a big shift in the assemblages right near that site, and I never see that. The other example that I will mention, I mentioned briefly about boron isotopes, which they're similar to water, but instead of responding to evaporation, they respond to pH. And if you were in a lagoon site near these springs, which have a low pH to them, you would expect a certain signal from the boron in the foraminifera, which would change if the spring were shut off. But you should also see that with in tandem with the other isotopes. So it's really this whole suite that each one might have multiple processes that affect it, but if they don't all zone in on the same answer, then you probably wouldn't expect a cave collapse. It should be more apparent when you look at some of these other isotope systems. But I haven't seen it, but it's an excellent question. That's something that has come up from my committee, actually.
So sort of the forum community. So you mentioned that the one that you were looking at has a broad salinity tolerance.
Yep.
So these others have more narrow salinity tolerances. Is that right?
Some do. So to look at this list, they have about 25 different foraminifera here, which is a wide range. There are about 4,000 species in the world total, but you don't always find so many living together. And again, they love this environment where they have a lot of carbonate to work with, and usually a lot of carbonate to work with. Some of my species, like these are known as the rhodolid group, which includes my species here of the foram. They can tolerate a wide range of salinities, and a lot of the ones in this lagoon can. But you have others, some of the melialids, for example, which have this football shape. They only like ocean salinities. They only like right around 35. So what you would expect to see if you get these shifts is that a lot of the ones that are common will still be present, but the ones that have particular preferences for really salty conditions or anoxic conditions, they will actually shift in their community. And so that's really useful because on one hand you can count everybody that's here, and I'll actually show you what that looks like and get a sense of what the community looks like. And then for the ones that are continuous, you measure their trace metals and their oxygen isotopes. So if you do get a change in more seawater or more rainfall, it should be reflected in the chemistry and the ecology. This picture here is from those assemblages that I mentioned, and this is if you take a sample of the foraminifera and you count how many of all of them are there. For example, an example here, you could count how many red heads we have in the crowd, or how many people have glasses, and have a defined set of characteristics that tell you about the people that attend science talks, for example. But then what you do is you run that through a set of statistics that plot them on this axis. Now, this is not a traditional XY axis. The math that goes through this actually looks at the entire count of organisms. For example, at every site you count 300 things. And what this graph tells you is how similar or dissimilar those communities are. So what actually matters here is the distance between 2 points. 2 points that are close together, like down here, are very similar to other organisms in that community. And counts or points that are far apart represent dissimilarity. And so you can see for each of these sites, these are just names of cores, but they are colored. Red is towards the ocean and blue is towards the head of the lagoon. That the ocean assemblages are different from the head of the lagoon. And so if you count all of these, you can actually see these shifts that generally follow salinity. And if that were true, then you should also see the same thing in all the trace levels. And so I've done this for the surface of the lagoon, and now I'm working on all of the cores to go back in time to actually answer the questions. Do we see changes in lagoon geometry? Was it always semi-enclosed and protected, which some forams like? Was it an open, active wave system, which other forams like? So we use those in tandem to answer that question.
So does that mean if you detect changes in the geometry, are you going to go back and record? You know what I'm saying?
Yes.
If you're assuming that you have a lagoon, when you have your linear collection of data points, but if that linear collection is not reflective of the past geometry of the lagoon,
correct,
will you go back and record?
I could. There are other isotope systems that we can use, though, to measure them. And in particular, one of them is the vegetation. So recall that I said the vegetation is very particular to the mangroves, like very specific types of environments and salinities. And that's true of the mangroves here, the seagrasses, which are very common, and what's known as suspended particulate matter, or just all the algae that live in the ocean. And this is a measure of the carbon isotopes. So the CO2 that they're breathing in, life is lazy. It likes to do as little work as possible, so you take the light ones. And this is a measure of the nitrogen to carbon ratios. And you can see that these three very common vegetation types have very distinct signatures. What that tells you is that if you go back in time and actually measure, you can see basically this looks like an increase in the mangroves in the system overall. So you would expect to see, is this a change in geometry, or did you, because suddenly the mangroves are enclosing part of the lagoon? Or is this simply an expansion of the mangroves in the site because of the groundwater? Again, if it's a change in geometry, then this trend would correspond to the foraminifera, which it does correspond a little bit. But primarily what you're actually seeing is sort of a steady increase in some of the salinity at this particular site, or excuse me, in the groundwater discharge, which these mangroves like. So you have to use them all in tandem. From everything that I have seen, I have not seen an indication of lagoon geometry change. And going back to some of these, well, this lagoon image up here, on the western side, which is the top of this graph, that's all hard bedrock. It's hard carbonate that we have no reason to expect has changed, even though the sandbanks on the outer side of it appear to have moved with currents over time.
Could you summarize the conclusions of your research in terms of climate change and what you noticed?
Yeah, absolutely. So with this whole system, what I'm really interested in is how does climate change on a smaller scale? Because globally, we look at increases in temperature when we think about how that impacts water. But as we can see, some places that are wet may be getting wetter, not drier. And some places that are dry may be getting drier. So what I'm trying to understand here is, going back over 5,000 years in the Yucatan, what is the typical rhythm of wet and dry periods in the season? Because as we move forward, the future climate will impact whether you see more frequent and intense droughts, which absolutely impacts water resources, or not. And so far what I've seen is that the periodicity is around 200 years for a lot of droughts, which has been confirmed in other work, but that it is it's a little all over the place for the last 1,000 years, which means that it is going to be very difficult to model the climate for the Yucatan in particular, which makes it very hard to prepare for your resources if you don't prepare for a worst-case scenario.
I think that's a great question to end on. let's
Great.
give Kyle another hand. Alright, well, thank you all for coming out to Science on Tap. I forgot to mention earlier, Kyle's actually one of our outreach officers at WISE. He does events like this for the public and actually does events in the local schools and things like that. And next week, or not next week, next month, the last Wednesday, we have another Science on Tap, and actually we have another officer, Zita, who's over here tonight, who's going to give her a talk on condors, right? Yes. So we'd love to see you back if you want to hear about some condors and their effect with lead, right? That's the talk, yeah. And we hope to see you then. Thanks for coming out, and have a great evening.
Yeah. Thank you so much for coming.